Ethanol in biofuel production has long been thought of as a supplement to conventional fossil fuel use due to their environmental benefits and to lessen the need for increased fossil fuel production in the future. The main source of this ethanol is the fermentation of starch to glucose. While cellulose from plants can also be used, it is much more difficult to make the cellulose accessible for hydrolysis as it is bound within the lignin cellulose in the cell wall. Both of these feedstocks, however, require significant land use in order to cultivate enough crop to meet fuel demand. Alternatively, microalgae can be used to create ethanol. Minimal land use is required for algae compared to that needed for crops, and there are also less environmental implications. This project focuses on the needs and implications of increased starch production for ethanol compared to the use of microalgae. Since the main feedstock for ethanol is starch, that will be the basis for data. Table 3 shows the ratio in change of price of corn to the change in ethanol production. The study was done by the Food and Policy Research Institute at the University of Missouri, and it generally shows that as ethanol production increases, so too does the price of corn. The same study also suggests that for every $1 increase in the price of corn, an additional 25 million worldwide acres of land will be needed to accommodate the 10 million additional bushels of corn that will be grown to meet the ethanol demand. The U.S. may not be able to keep up with some of these land requirements as land is limited and 20% of our current cropland already goes toward the production of ethanol. Another environmental implication to consider is changing an ecosystem from its natural state in order to accommodate a crop. This has the potential to release 100 times more carbon dioxide into the environment than the reduction in atmospheric CO2 posed from their combustion compared to the combustion of fossil fuels. An example of changing an environment is taking a rainforest and making it accommodate a palm oil crop. While palm oil crops require the least amount of land compared to conventional feedstocks, they still require twice the amount of land needed for the growth of microalgae. Land comparisons can be seen in Table 1. The final part of this study that shows the negative implications of increased starch-derived ethanol is the negative correlation between the decrease in the products from livestock to the increase in ethanol production from starch. The main reason for this is that the increased ethanol production causes higher corn prices, leading it to be more expensive to buy feed for livestock. This has worldwide consequences as the U.S. produces nearly 60% of the worldwide corn supply, but can use as much as 18% of this production for our own ethanol. The International Food and Policy Research Institute Director General Joachim von Braun from 2008 stated that a too rapid expansion of biofuel use could cause areas of the world with existing hunger problems to intake 8% less calories daily, while most areas of the world would see a 2% decrease. An alternative to this that solves many of these problems is using microalgae as an ethanol feedstock. One main advantage is that conventional feedstocks may only convert 0.5% of light into useful biomass during growth, whereas algae has the ability to convert up to 10% of light. Not only this, but they can be grown continuously in cultures compared to needing seasons for crop production and generally require zero or significantly less pesticide than that needed for crops. The growth of these algae are in two main types of reactors. One bioreactor is an indoor single-species algae community, whereas the other is an outdoor pond reactor, which holds some advantages. Namely, exposure to the environment gives rise to biodiversity and the potential to produce more useful biomass. Although zooplankton will also be produced, and as they are herbivores, this will decrease the amount of algae produced, and this needs to be controlled. As far as land, microalgae growth only requires relatively flat land in ponds that would not exceed 4 meters in depth. Its comparison to conventional feedstocks can be seen in Table 1. And based on this, if algae were to account for half of the transportation fuel in the United States, it would only require about 3% of the current agricultural land in use. This was a study done by the University of Kansas. Algae can also be used to treat wastewater that contains heavy metals, heteroatoms, and nitrogen and phosphorus, both of which it needs for its growth, that would otherwise be absorbed into the ground. Waters can also be recycled for algae growth with many less variables compared to crops such as irrigation systems and crop rotation. A second advantage that is not fuel related would be the use of predatory fish in order to control zooplankton, which would give a benefit to the ecosystem. As far as fossil fuel use goes, it doesn't hold any advantages over conventional feedstocks, as both are limited, and for algae it is generally limited to using natural gas for drying the algae. While all feedstocks have their advantages and disadvantages, using algae as a main feedstock for ethanol would ease many of the food and land concerns that we currently see from conventional feedstocks.